Hello, test. Can you hear me?
Yes, we can hear you.
Thank you. Welcome. Yes, let me set up. As usual, in the first few minutes, if you have questions, do not hesitate to ask me. Check if Gita's here. I think Gita's haven't arrived. So.
Hey, Tim, I have a question.
Yeah, who's talking?
Yeah.
Li Jian?
Yes. Yeah,
okay.
Legion. Yeah. Just want to know, would you arrange any consultation during the Steelback?
No, not in the Steelback. Well, this said.
Because next week is Steelback, and the assignment 2 or 1 is due in a week after the Steelback. Yeah. So
okay, why not? Let me see. I will do Wednesday office hour, which means Wednesday. I need to mark it. Give me
Thank you.
Because otherwise I promise you, but I just forgot it. Then that is
because I know it's like a Steelback, and you're supposed to have a break.
No, after this session, we'll have a 1 hour Q&A. Let's do that in the next Wednesday. You do not need to book it. I will just be here.
Okay.
Answer questions.
And would the link be the same as the workshop, the lecture?
Yeah. We just reuse this same link.
So
okay. There's no drama.
Okay.
Yeah. And okay, Isaac. As a return for answering your question, I make you the co-host.
Okay. Yeah, sure.
So because I cannot overview the session, now you are the co-host. Help me to admit people when they arrive a little bit late, and I just ignore their arrival. So please let them in the session.
Yes.
So, yeah.
But I'm actually using my iPad. I'm not sure if I can do it or not. Let me log into my desktop one, and you can assign that one to the co-host maybe.
Yeah, when you do that, raise your hand so
okay.
I can know. Oh, okay, Isaac is ready. Okay.
Yeah. Okay. Yeah. Happy to do it. Thank you.
Thank you for the help.
No, right.
In the assignment. I have another question from Rajit. Sorry if I pronounce your name wrong. Yes, you can use all the helper functions in the scikit-learn. I think if you review the implementation demonstration I have done in the last week, I would say I did a pretty good example of completing the assignment. I have used the split functionality, and if today we have more time, I can make the statement more explicit. Because, for example, if you decide to go for more advanced models, such as the ensemble method or the neural networks, so some of the basic computation can also be saved, but the principle is that you cannot forgo the essential core algorithm of whatever you want to implement. Okay. No, the starting will be 5 p.m., not 3 p.m. I have already other commitment at 3, but after the working hours, I think from 5, I would be freer. Well, let me mark it. Let me mark it. 5 p.m. And I will, yeah, I will take a note of this week's announcement as well. Oh yeah, let's share my screen. So you can see my screen right now, okay? Everything, every window starts mess up after I start sharing the screen. So yeah, I create an announcement and see. Okay, next Wednesday, 5 to 6 p.m. Extra hour. So okay, mark it. Okay, thank you, Isaac. But I kind of lost the audience here. Okay, it's here. Got you. Thank you. Well, we are several minutes into the session. Let's start. As usual, well, going to review some of the important concepts we have learned during the semester. This is always it's always easier to get started when we are on the same page. Session 7. Okay. Oh, you have. I have another question about the class notebook. Okay. Let me try to fix right now. Let's see if any technical issues here. Okay. Call up. And not this one. I'm opening the notebook of this one. So let me share. Anyone on the internet? Link copied. Can you try the link I have just posted in the chat box? Okay. If that works, I will use that link to update the Canvas site. Okay, thank you. So okay, updated. Let's see how it works. Well, let's start our discussion. I hope before the Stilwec, I do not give you too much load. And in today, today is a kind of a reflection session. Uh, we start from considering what we have arrived here. Okay, in this subject, for the first 1 and 2 sessions, I got some small issue here. We start uh, by introducing machine learning as an ambition, our ambition to let the machine to program themselves from experience. We call that software 2.0. And to achieve this ambition, we consider there are 3 conditions for any machine learning project to be feasible. So we need the experience, which is data. We need to believe there is some trend or pattern in the data to be discovered and can be generalized outside the samples we have observed. And thirdly, for feasibility issues or economics issues, we apply machine learning mainly in the situation where we do not have explicit mathematical description of the trend. If we do, we program. We do not let the machine program themselves. And in the second session, we consider the data because the 4 elements in the machine learning tasks. Here we adopt a framework which consists of 4 elements: the data, of course, a hypothesis family, and we understand this family is as a limiting factor, which prevents us from imagining any kind of relationship in the data. Because in this subject, we are mainly trying to get a trend that helps us to map from some observable data attributes to the target value, which is called supervised learning. And we restrict ourselves from imagining any kind of this relationship. We only adapt some regularized relationships. And we have a selector to pick up one well-behaved hypothesis from this family to represent the learned pattern. And the well-behaved or ill-behaved is according to some criteria. We call that loss or risk or error or whatever cost. Okay, so data, hypothesis family, selector, which is algorithm, and the loss are the 4 elements. And please remember, I was manually acting as this guy in the second session to select things from a spreadsheet. So in the third and the fourth session, we studied our first machine learning model, a model family, the linear family. And the main point of that idea is, let's treat things in a simple way. Given a data table, let us consider each column of the table, which means by a column of the table means each row of the table will have its corresponding value or at that column, and we call that data attribute. Okay. We link that to nodes in such a model and give it weights. And we take the weighted sum of those attributes, arriving one number, and we think this number summarizes everything that is relevant to the task. We then use this number to do something. For example, to compare it with a threshold and use that for classification, which is perception. So this is a generic linear model. And in the next session, we study geometric point of view of this model. So we consider the data points as vectors and the width also as vectors. And this first do element-wise product in multiplication and then sum them up. This operation can be understood as taking the inner product between two vectors. Then we have acquired a geometric point of view of that, taking the sum of these weighted sum of these attributes and summarize that in the number. This strategy as well, coloring the data space in a gradient and decide according to some constant color here. Okay, for example, making a classification boundary. And we have mentioned that this kind of geometric point of view is ubiquitously useful in machine learning. Okay, in the fifth and the sixth session, we considered our second machine learning model, which is the decision trees. We first established that this similar to the linear model also was motivated from very intuitive, natural motivation. We just want to make the decision about the data sample by using if-else branches. We use a series of if and else statements to make decisions about individual data samples. And what is the more sophisticated here is we want to implement this structure to fit our scenario, our theme, that the whole thing needs to be coded up by the machines themselves, rather than we explicitly writing out the if and else statement. To do so, we constructed a tree node structure. Okay, and constructing the tree by programming it up at each node, we either arrived at a consensus set. We now have some agreement about the target value, which means, okay, after so many conditions, now I am in a situation when condition means cut the data space according to a test of one attribute, and maybe when select this part, we can cut again here and cut again, finer and finer, until we have reached some region that the target value in this region is pure enough. So we are happy to return some decision. This is called decision trees. Decision tree, and alternatively, we might want to cut again to achieve. We might want to make further test again until we have reached the consensus, which we have just mentioned. And to select which data attribute to test and how to test requires a measurement about how pure the target value is and answering the would-be question, like the what if question. So what if I split the data population according to a candidate attribute to be tested, and using that condition, if I do so, I would arrive subpopulations of the data, and how to measure the purity in the target value of the original population and in the subpopulations that would have been resulted if I test I do a testing according to some condition of on a data attribute. Okay, so we then introduced the information theoretical threshold criteria. We consider how to measure the information in a random variable, and how to compute the contribution of the knowledge, knowing the knowledge of one variable. This will save us from encoding the y of this amount. Okay, so that is what I have arrived here, and I did a little bit more detailed review so far because in today's lecture, the main point is for us to do some reflection of what we have achieved so far. There is only one take-home point. If you'd like to, I apologize. Guitars, I have accidentally lower your hands. Can you raise your hand again and I make you a co-host? So I kind of try to maintain the, yeah, thank you. So there is only one take-home point today, which I want to attack it from different angles. The take-home point is, well, shortly put, learning is a random business. The result is not guaranteed. And we have some confidence about it. So there are 3 points, but all in one sentence. Are somehow guaranteed, somehow confident, but ultimately random business. And that is learning. Okay, this discussion is very weak. I'd like to invite you to consider it from using examples. So let me show you an example of what do I mean by learning is a random business. And first off, another very important part, I put it here. Maybe you have already somehow appreciate the statement that learning is stochastic, is random, but I'd like to invite you to think, what is the main source of stochasticity or the randomness? I put it here. Why this is fundamentally stochastic? Okay, keep this question in mind, and let us start by looking at some examples. Okay. And this notebook will be made available to you very soon after the. Okay, why not? I just make it available right now. Sure. Okay. I put the link into the chat box. You do not need to follow me right now. Yeah. Do not let the code distract you from follow the discussion, please. So in the first place, I'd like to perform learning using a simulated random situation. I will let you see what I'm doing. Okay. The first I'm going to do is a very interesting thing I show you. Just to test if my environment is ready. Yes, it's ready. So I'm going to do is I will not use all the training samples I have. By the way, we are just use our old friend Iris data, and we do the two-class classification problem. I will split my training data further. Okay, and I will throw away the most of that and only take a small sample from my training data. Okay, so I throw away the second part, which I said I will use as the test, but I just throw it away. And SS for subsample. By the way, if anyone find it's difficult to read the characters on my screen, let me know. If it is okay, I just want to make use of my screen space, okay? And you can see what we have now. And in this example, I would just use a linear classifier, but instead of using the perception we have learned, I'm for the purpose of demonstration, I will use a more reliable one, which is the logistic regression. And here is also an example. After you graduate from this subject, and you have acquired all the knowledge and confidence of machine learning, and you have decided to adopt machine learning models in your workplace projects, how easy it is to construct a model. So let's see, from scikit-learn.linear model import logistic regression. Okay, and let it to be an instance of this class and fit to the data and done. Okay, be noted that that is exactly what we do not allow students to implement a model. This will not count as an implementation in your assignment 2, okay? But now our focus is not to implement the model. We just use this as a linear regression, not regression, logistic regression. It is a kind of a linear classifier. So let me visualize the classification. Okay, not very surprising. However, you may have noticed that, well, that boundary looks a little bit funny. Why? One reason is because the range of the space that's been drawn is different, but ultimately that that is because we have used only 15 samples to train it, and the result is unstable. Okay, um, let me do the experiment for multiple times. See, here we randomly sample a subsample of the models of the training samples. See, I print out the first sample to show something. Uh-oh. Simple. Sorry. There are 75 samples, and we take 20% of that because we said 80% will be used for test, and we actually did not do that and just throw them away. We keep 20%. Now, the first one is this one, and if I run it again, you may notice that the first one has changed. That is because the sampling is random. Okay. Well, I can still take the random sampling, but have a deterministic but still distributed uh, a subsample by giving it some random seed. Okay. If you have questions about this, let me know. And in the code, I put it here. It's just to let the result repeatable. But from the statistical point of view, it is still randomly distributed. I just want my program to be debuggable. So I set up a random seed. Therefore, in each of the test or experiment, I will have the same string of random numbers. Okay. So this is what I'm doing. And I'm doing that for 4 times. And let us see what we have. Okay. Now, please notice that the triangles represent the sampled training samples, and the original ones, it is not very obvious, but if you look at closely, you can find the triangles. These are randomly sampled subsamples that has been used in this round of training, and those circles represent the original ones. But the important point is here. I would invite you to notice that the classification result is different from time to time. Did I make, is it different? Let me look. Oh yes, it is different, although not as much as I expected. So I'm arranging my window so that I can give you a more accessible view of the result. Okay. Let me try to make this very explicit by copying this. To here, okay. And I'm doodling the data space and the classification boundary here. Okay. Second one. Okay, you can notice that these lines are not exactly aligned. This is not superly obvious here, but you can notice that for some of the training samples, they are misclassified by some of the learned classifiers, but not the others, like this guy. See, this guy here, and it's different, okay? And what I'd like to invite you to think about that is, look, if you consider the whole process of learning, we get the data, then the data is given to an algorithm, and the algorithm is selecting a linear classifier model, which means the weights of the classifier, by comparing by according some criteria, okay, and eventually it produce some learned model. And please try to consider a point here. So this may not be present in any of the training data set. This can be any random position here. It is more easy to understand if you imagine the location that is not in any of the training data set, but near the boundary. Okay, if we consider such a location, let's call that some X test. And if we apply the learned classifier on the X test, so what results would we expect? Some consistent classification? Probably not. For some region, some of the learned classifiers would classify that as positive class, and some of the classifiers will classify that as negative class. So in any event, we can expect the result is not consistent. It can vary from time to time. Sometimes we perform exactly the same. We can control this part, okay? We can control the algorithm. We can control the loss. We can use a particular learning. We can use a particular hypothesis set as we have done here. Okay, we use the same we use the same model family. We use the same learning algorithm using the same criteria, but still the result of applying what has been learned on a test sample can be different. So I would like you to imagine, where is this randomness coming from? Why this is random? Okay, while you are thinking about this, let's see if I have explained things clearly. Okay, I'm very happy. Many of you have followed along. So can anyone guess where is the main randomness from in the learning business?
Excuse me, could you please repeat the question?
I'm repeating is, look, in my program, so starting from line 10, this line, I construct a model, okay? What happened? I construct a model here. I train the model here, okay? Both any factors in the training, I haven't changed a little bit. And the model I've used is from the same family, okay? And with all this, why I have different results when I try to apply the trained model on the data space, on everywhere on the data. So maybe you can consider this guy. Okay. In this round, it has been misclassified. Okay, it's belonging to the yellow class, and in this round, it has been classified as a purple one. And in this round, it hasn't been misclassified. Why? Why the result of applying the same algorithm and following the exactly same procedure, why the result is different when we apply what have been resulted from the learning to the particular test sample?
Because each time you choose the test and train data set is random.
Okay, yeah, it's not about the test, because if you consider other points, the test point hasn't been changed. What has changed is here. Remember one story we have told before multiple times, but we haven't emphasized, is this is essentially a black box we cannot access. This will give us samples Okay, in the data table, and with the answer, so x first sample and y first, x2, y2, and this training data set, this set is a random set. The table, the content of the table is random. And there is where the ultimate randomness from. The learning process is a random one. Okay, I hope that explains things more clearly. Well, we can see things more clearly by maybe reduce the test size, and then you can see with even less sample from here, the behavior changed according to the training data even more widely. So yes, you can see some of the training samples. Sorry, some of the in some of the cases, the classification boundary changed largely from the others. This is more obvious. Okay. I got a question. What is the black box mean? You mean this box? This is just the mean the possible data, the range of possible data. Look, now each of the dot, each of the circle, either the circle or maybe I make it a little bit enlarged for you to see clearly. Okay, so each of the circle or the triangle that represent some data. See, here and here, you get sorry. This is a data sample represent one flower. And that belongs to the yellow class. Okay. There's nothing to stop a flower in the wild just grew to be at this point. Okay. This is neither in the sampled subsample nor in the training sample original iris data. This just represents a possible iris flower. Nobody can deny that there is a possibility an iris flower just grew to be like this, right? So when we build data models, we ultimately need to care about those positions that we haven't seen but possible. So is that clear?
Yeah, sure.
Okay. So now we have appreciated that training is ultimately a stochastic random business. And now in the next step, we will go further in this line of thought, but consider an even simpler example. So look, now let me mark the deterministic steps. Actually, I have already marked most of that. So let me maybe do it in the here. So here is data and learning from H according to some loss and some X test terms. Let's just focus on this particular test, not anywhere else, just this one. Okay, now we have everything here fixed, right? Sorry. Yeah. So unfortunately, the final result is still random because this is random. This is random is because the input to this entire process is random. Okay, sure. Let us consider this as an estimation problem. We can reframe that in this way. See, you can just imagine the problem like that. If if I have an observation of some underlying positive and negative distribution, I observe these samples and I want to make a prediction here. And of course, my prediction is depending on what samples I have observed. Okay. Well, to study that in a more quantitative way, in a more quantized way, let's consider an even simpler situation. Okay. See, what we have observed is just real numbers. Stuff like that. Okay, and what? Sorry, I wouldn't say we have observed the random numbers. I would say I would explicitly explain the setup of the experiment. It will be clear later. What I'm going to estimate is just the mean value of a distribution. So is this simple enough? So basically, I'm not saying that these are random numbers. What I'm trying to explain is, see, I have a jar. This is a very ugly jar anyway. So I have different color of balls, balls in the jar. So maybe they have some ratio between them. See, then I take samples from the jar. Okay. And I want to estimate the ratio of any color, maybe red. Sorry, ratio of from the samples. Here I get 0.6, which is fortunate, but it is also possible maybe this guy happened to be green and I have 0.4 in this case, which is wrong. Okay, let us set up this this simpler than learning example and to appreciate the variation in random estimation. This will also motivate the next week's study. Okay, so let's I mean the next session's study. Let's look at the code. So what I'm doing here is I'm going to use a random generator. A random generator is a thing that you use to generate random numbers. Okay, now with that, I can call that. I can call the RNG, give me a random number. Then you get a random number. Again, again, again. And let us try to convert the random number into a 0 or 1 random variable. So it's easy. By the way, this guy is uniformly distributed between 0 and 1. So now you have just a judgment of true or false of the random sample to be less than 0.5. Okay, and I can convert that into integer. Now I have zeros and ones. Now you notice that there is an essential parameter controlling my, this is called a binomial distribution, which means you have binary outcomes. So this distribution, well, just has a fancy name called binomial. And there is an essential parameter in the binomial, which is to which threshold I'm comparing. Of course, if I'm comparing it to a very, very small value, and you can see it is rarely this could be true, and most of the result would be 0, 0, 0. Okay. And vice versa. So this parameter can choose how likely the binomial distribution is ended up with giving me a 1. You can consider that is the true ratio between the two colors here. Okay. So what I'm doing is try to estimate this guy from random samples of this experiment. I'm just trying to, let's make some reasonable parameter, maybe 0.4. So this is a list of this. Of course, this list has only one element. Okay, but to construct a list, you can let Python to do that for multiple times. For multiple times, I in range maybe 10, do 10 times, and look, I is actually a useless variable. It hasn't used anything. It's just to control the construction. You need to do multiple times. So I just use this This is a convention. That means I do not use this guy. And if I take the mean value of that, that gives me an estimation of the portion, the ratio, the frequency of the outcome to be 1 in my experiment. And now you can see that, well, this is not such an accurate estimation. We have missed by 10%, right? And you can appreciate that this estimation is always stochastic, it's always random, it's always has some link to the true value, but not exactly to be the true value. Okay, so this code cell just did what I has. Sorry, we have said. Okay, I haven't set up this parameter. I happen to call this parameter true risk, and you will know shortly why we give it such a name. But anyway, it's just a parameter. Now it's 0.3. So, and the estimation is 0.4. So what we are going to do now is to investigate. Okay, look, now we simplified this. We have simplified this into one thing that, okay, we just count the number of ones rather than doing all the learning, selection. No, we just want to understand the essential randomness. I have a random population and I'm going to reach some result from the random population. And I want to investigate how much confidence I can have with respect to my about the result I have reached, I have extracted from the random population. Well, our experiment is very simple. The population will just be zeros and ones. And our task is just to estimate how likely, underlying likely, the ones to be the outcome. Then we just count the number of zeros and ones. Okay. So what I'm doing is I will perform this experiment to take 10 sample population and estimate the underlying probability of having one, or the underlying ratio between the two colors. And this, if I call this one experiment, I do the experiment twice, 20 times. Okay, like this. This is one experiment. This is a second experiment. I would need to remind you to link this to the learning situation. In the learning situation, we will have only one experiment because we have only one training data. And here in this study, we are going to appreciate how the randomness in the training data would affect this entire process. So we create a toy example in which we can perform from the omniscient God point of view of estimate the randomness by taking unlimited number of training samples. In practice, we only have one row of this example, and you have what you have, and you estimate what you estimate. Okay, and our purpose is to investigate the the error, the risk, the variance in this estimation. So you can see in many cases, it is estimated as 0.3, which is correct, but sometimes it's different from that. Okay, let's visualize the variance in this set of experiments. Okay, so this is quite discussion. Okay, and you can see in these 20 experiments, well, we have arranged the estimation of the mean value from the 10 samples. Okay, I think I can draw this more clearly by doing the experiment not 20 but 200 times. Okay, this time is the viewpoint is more clear. So about this is median value, which is accurate, but please be reminded this median value only comes from these 200 experiment, and in practice you have only one. You live only once in real life, but here we take the Gauss point of view. If you live many times, if you do many training process, you have half of the experiments get overestimated. You get half of this experiment underestimated. Okay, but on average, you get somehow accurately estimated. And the range of variance is huge here. Okay. And by the way, if you read the code, this mean axis is 1, just means you take this 0, 1, 0, 1, 0, 1 table, and this is axis 0, this axis 1. So you take the mean value in this direction and you get the mean here. There are 200 values here. And in the next part, we just do a very obvious way of increase our accuracy of estimation, which is also impractical, just for the purpose of investigation. We increase the number of training samples, observed samples, okay? And you can see that in this case, the variation is much, much smaller, from 0.27 to 0.32. And that is the whole range of it, okay? And the majority is concentrated even more. Okay, we have just to do a lengthy discussion about the uncertainty in learning, in more than learning, in estimating something from a random population. Okay, there is some underlying truth. We have a very reasonable or the correct way to compute the underlying truth. The only thing between us and the truth is the fact that we do not have the direct access to the underlying facts. We only have access to some random samples that has been drawn randomly from the underlying facts. And we can only apply our methodology, technology on those random samples. And hopefully that will give us some estimation about the underlying truth. So that is the fundamental challenge of machine learning and in statistical estimation overall. So this is quite a bit. Let me relaunch that. See if everybody follow along. Please take the time to let the argument think, settle, and if you have questions, please ask me. So that is the take-home point today. And in the remaining part of this session, I hope I can demonstrate to you how beautiful this argument can lead us to. There is a like a intellectual gem, gem in the machine learning field, and I'd like to introduce it to you. So I still have a few. Now we have more than 80 people. Maybe some people need some time to decide whether they have followed along. So I'll give you maybe 2 minutes. Okay, I grab my coffee. This is quite a bit of talk. So excuse me for a while. Grab some water and think about it. Okay. I'm happy still we have slightly most people follow along. Let's go. If you have questions, please please ask in the chat box. And if you still feel confused, you can stay for a little bit while long after the session. Well, next, coffee power discussion. We have considered that learning is learning essentially if you focus the ultimate outcome of a learned predictor on any kind of input that will be an estimated stochastic quantity from a set of random samples. We have established that. Now we will consider an ultimately important quantity to be estimated, which is how much error the predictor is going to make. Okay. So let's consider, in this case, I'm, okay. Maybe, let me draw that, okay. So, okay, maybe let us use this as example. See, the training samples in this case are triangles here, here. In the training set, those triangles, this boundary does not make a single error. Okay, we can see error evaluated by this hypothesis on data. This is 0. However, we know by fact that the error, the hypothesis, the learned hypothesis will make when we deploy it is more than 0. Why? Because it's already made one error here. Okay, this guy. Will be an unhappy surprise to us. And please imagine, according to our previous discussion, every single dot this can all be some potential flower samples, which we had never seen, and we do not have access to anyway, because we haven't. We will not go to the field and just to sample every single iris flower in the wild. That is, well, totally impossible. So please appreciate there is an ultimate golden standard for the classifier. That is, what would it have if we apply that on the wild population? If we consider that golden standard as the correct incorrect ratio in the jar, then this will be the one that we can calculate from the observed samples. Okay, now please remind me again, our focus, the color, our focus, our quantity of interest now is no longer whether the positive class or negative class or yellow class or purple class the predictor has produced, or the underlying class is. The focus is whether a predictor is making a correct or incorrect prediction at the data sample, the data on the data population. Okay, so we are interested in these two values. We give them names. Let's call this. More explicitly, we call that E in, which means the error computed in the training samples. Okay, for the hypothesis. And we call that E out. For an H. Well, what we try to consider is, well, let's see. What we definitely do not want is, if they differ from each other too much. See if this is 10%, which means, okay, in the data sample, you have evaluated with some error rate, but when you deploy the learned model in the production environment, then you find yourself in a surprise. That is generally considered a bad thing. So now we do not distinguish happy surprise or unhappy surprise. As a reliable engineer, we just don't like this kind of surprise anyway. Okay, this is a bad event. This is a bad event. Well, please be aware, this bad event, this event itself is a true-false event. This is a binary event. It happens or it does not happen, right? And yeah, then it comes our previous central point. Who or what can choose whether this event happen or not happen? I give you a poll, and you can appreciate. You can express your understanding so far and thinking about the question. So, look, I have discussed. Now we consider an event, and that event is a bad one, which means a hypothesis. For example, a classification boundary here, and this boundary is a hypothesis. This hypothesis makes maybe 7.3% error according to the observed data. And I'm considering an event. Is this 0.3? See, this is maybe too much, 0.01. I'm considering an event. Is this 0.3 too much or too little an estimation of the error that H would well make when I apply it to the data space, to the training, to the test data? Okay, I have fewer people following along, so if you have any doubt, I please invite you to try to ask it. It's super helpful if you just try to express where you don't understand. Even you try it and you find you stuck at some point to articulate your idea into some reasonable statement, then probably you find the important confusion in your understanding. So for people who need to think more or need help, please try to speak up.
Hi, Professor.
Hello.
Actually, I don't know what this function means. The E in subtract the E out.
E in means, okay, I zoom that out a bit. Look, the E in means the error calculated, assessed, evaluated in sample. Here, it is 0. Give you another example. Here, it is not 0. It makes some errors in the training sample. Look at this guy. In the training sample, it has been sampled to give it to the trainer. Look, I would like you to classify this as purple. However, at the end of the day, we arrived a classifier that classified this as yellow. So in this case, the E in is not 0. And in this case, the E in is 0. So that is E in. And E out is an unknown thing. It's a conceptual thing. That is our imagination. We would like to see if we have applied that classifier, that hypothesis onto the entire data population. That includes the data we have sampled, the data we haven't sampled, the data we haven't collected, the data that has existed before and lost forever, the data that's going to be. So all the possible iris flower, we include everything, and we apply our classifier on this everything thing, we will get an E out. This is a mind concept for discussion. This is not accessible practically. Okay. So anyone can come up and tell us if this bad event is happening at some times and not happening at other times, what can choose whether the bad event will happen? So, okay, because this H, the hypothesis or the classifier is given, is fixed in this discussion, we consider the classification rule of this line and we fix it. We always discuss this line. This does not change anything. And the out H, as we have said, that is an all-inclusive data population. So applying H onto this everything population, the result is a fixed one. This does not change either. Okay, so basically this is a constant but unknown. And these changes with respect to, if you recall our discussion above, these changes with respect to what we have let the learning process have observed, given a different data, a data set, the learning will give us, sorry, I don't mean the learning. I don't mean the learning. I mean the estimation, because we are talking about the same H here. So given a different data set, the estimation of whether H has made errors on the data set may change. So the randomness comes from the random data samples. Okay. Maybe you can imagine this way. Say in this class I draw a lot of spaces, but for however simple or however complex spaces, your tutor is not a very good illustrator. So I just use some boundary to draw. Well, let's consider all possibilities here, but let's consider a magic space. Okay, the possibilities I'm considering here is really complex. Each point represents a sampling of n well, samples. So that represent x1, y1, x2, y2, xn. Okay. But let's see. I just put maybe well, a symbol here to distinguish this bag from the other one. So this may be sampling another bag of n samples. Okay, x1, y1. And let me put a square here. Please be aware that in this illustration, I just try to distinguish different bags. That does not mean, do not confuse this with the space of the data. Okay, it may well be like the second sample here happen to be the fifth sample here. That could be the case. I just mean that can be two different bags. Okay. Let's call that maybe capital, well, calligraphic D. Well, each data set is from here, okay? And you can see, because each dot here represents n samples, you can compute an E in from this particular bag of samples. So, well, I just do not want to make more narrative talking, but you please try to imagine this is a bag, and that bag, how to draw a bag? Had a tag on that error, and this is another bag. This maybe have another tag on that bag. Okay. Well, what this is, those tags can be different from the real error rate. And the beautiful thing here is we have some kind of guarantee from the estimation from the bags will unlikely to be different from the true error too much. How? Well, if we put a probability here, that is the probability bad thing happens for my H. So the H is here. Okay, now with respect to H, we can maybe have good bags and bad bags. For the good bags, we see, for example, if this is a good bag, if we evaluate H on these n samples, okay, and the result of the evaluation is close to the true error rate of H. And therefore, when we get some performance evaluation of H at this bag, and deliver that, we will have confidence that, okay, I'm happy that in future H will perform more or less consistently as evaluated. And maybe this is a bad bag. If we have evaluated H on this, but in future the performance of H can be very different from what we have seen on the training data. Okay, so if we color the entire bag set, we sometimes for some bag sets we see, okay, this is a bag set, this is a good bag. So notice this color is not say that this is correct or incorrect. This is just to say, okay, using this bag and that bag, we will have accurate or inaccurate estimate of the error. Okay, and this is the probability of having this bad event, or we happen to sample a bad bag of samples. This probability decreases with respect to n at an exponential rate. So, well, that looks a little bit scary. Here is a quick interpretation. Don't worry about this epsilon too much. Consider it as whatever you want to guarantee, such as 0.01 or something. Anyway, when it's fixed, it's fixed. Just remove that from the equation. So I'm not sure if everyone has a very solid mathematical background. I just treat you as street people. So let's explain the exponential decrease here. Okay. See, like if I'm talking about this okay. I'm talking about these two species of bags. And if according to some calculation, say I would have maybe 0.4 chance to encounter a bad bag in this experiment setting. For example, if I'm taking 100 sample, I will have 40% chance of having just have a bad bag here. Then by just taking 200 people, 200 sample, I would have 0.4 times 0.4, 0.16 chance of having the red bags for that hypothesis. And this argument goes along this way. So you can imagine the chance of making errors, the chance of encounter surprises drops exponentially with respect to the number of data samples. So this equation is called Hoeffding's inequality. It belongs to the family of, okay, anyway, does not matter too much. So what is important is this helps us to get confidence about learning. But that is not the end of the story. I know I have no time to fully expose you to the full glory of the theorem. Just to remind you, there is a another huge obstacle in front of us if we want to use this line of argument to get confidence about the learning, which is that all the argument applies to this edge, a given edge, an arbitrary edge. When it's given, it does not change. Okay. However, learning is about to select from a hypothesis set. So intuitively understanding is that maybe some bag is bad for this edge. And we can, by increasing the number of samples so that the red bags, the ratio of the red bags, the portion of the red bags decreases rapidly, so much so that the red bags takes so little area in the experiment space. Then given the H, we are very confident about the performance of the H. However, this is not learning. This is just a test H. How about if I end up with an H? Okay, I see, congratulations. I'm very confident my H will make 45% of errors in production. Well, you see, the confidence is high, but the usefulness is very low. By learning, we need to select among a lot of hypotheses and find one that is the best in our candidates. And unfortunately, maybe for this H, this part is the bad bags. And for this H, and for this H, maybe this part is the bad ones. And for this H, maybe this part is the bad ones. Then by considering the bag of H's, the hypothesis family, we will get back to the situation where there are a lot of unreliable in evaluation, so much so that after we have selected H, we have no confidence. We have no confidence that if the selection happens to be on a bad bag of the selected H, and after the selection in production, we happen to enter some unhappy surprise. Okay. Well, there is an argument to confine this possibility as well. And at the end of the day, the glory is, well, as long as the diversity in your H, so which means in the family of H, one H does not behave superly different than the others, then you will have a guarantee that this probability of the selected H will eventually drops with respect to the exponential of this times a factor. A factor. Let's just use a symbol to represent it. That is proportional to the maximum different behavior of H on 2n samples. Okay, but this is a mouthful to swallow. So if you are interested, you can come to my office hours, or you can stay to ask me questions. And of course, you need some other adjustment of the parameter anyway. Okay. So I don't think I have enough time to demonstrate all the code today, because I'd like to guide you through the quiz. Okay. So after that, in the QA time, I can show you more details about the discussion. And before to do the quiz, I just quickly remind you, you can book my office hour using the table here, which is in the FAQ, I think. And also, please heed that the extension for assignments is application based, and we do have rules of application. You cannot give me last minute application of doing the extension. Please heed that I have made an announcement last week, and I think I will do a reminder in this week. If you need extension, apply, or you apply urgent, or you need to appeal. Without applying, you can see the rules here. Okay, let's go to the quiz. Okay, the first quiz is just repeating what we are talking here. It's a bit theoretical, but basically there are two main things. One is E out is unknown and cannot be computed. It is a concept for discussion. It's unknown, constant, cannot be computed. Okay. And E in, I'm putting an N here, means E in on N training samples, which can be computed, but it is not a constant. It depends on the samples. So E in is a random quantity, varies with data. So be noted, there are two options in this, two correct options in this question. E out, unknown, constant, cannot be computed. E in, random, can be computed. And this is a bit lengthy question, but just to remind you something about the learning criteria. So which is basically very simple, actually. The L, we haven't get much chance to discuss L in the semester. Well, the L should have some mathematical property that is helpful in for the selection algorithm. And the question here, you can read it back home. It discusses a very common trick to for the classification tasks, because classification task is well, essentially discrete, categorical, non-continuous. You correct, you incorrect, you get an error. There is not much middle land in between. And that creates a situation. If there's no middle land in between, and if you want to change, you do not have a global solution to your model parameters, and you want to make some little adjustment on the parameters and see if I adjust this, how would that improve my prediction? However, now your prediction is assessed in a 0-1 basis. There is no improve, just a sudden jump. That can create a problem. And we have one of the clever method in the perception, but that does not scale very well when the data is very large, and it's not very stable either. So modern learning methods always adjust the parameters bit by bit. So we need some measurement about the improvement in the bit. And that question says, okay, for classification problem, say if we have three classes 1, 2, 3 to predict. One way of measuring that is let the classifier to predict probability of a sample belongs to one of the classes. And we take the logarithm of that. Okay. And see, the less you have predicted, the greater magnitude of the negative value of the logarithm. Okay. And if you take the negative of that, that will become measurement of how wrong your model has been if the correct class happen to be this one. For example, if you predict there is only 20% of chance of the sample belongs to class 1, and the truth is that the sample happens to be class 1, then what you have made the prediction is very poor. You have only guessed, let us see, 20% degrees of correctness. So we give you a punishment of negative log 0.2, and you can do some numerical calculation back. Say, okay, the less probability you allocate to the correct class, the heavier penalty you will get from this loss. So that is what is instructed here. Well, it is using the first cost, and there are two situations. One is the prediction is 0.033, 0.33, 0.34, and the true class is this one. And the other one is another prediction, but this is the true class has the highest probability, and the true class is also this one. So in the 0-1 evaluation, this has a cost 1, okay? And this has cost 0 because this is wrong and this is correct. So you will choose 1, 0 in 1 and 3, 1, 0, 1, 0. Okay, and in the second way of measuring the cost, here you have the cost of negative 1.8. Okay, sorry, negative 1.11 because that is 0.33, and here is negative, which is positive 1.8. So this should be 1.1, and this is 1.03, 1.1, 1.03. So this one, okay, 1, 0, 1.1, 1.08. Okay, the last one. So that means that discuss the noise. We haven't much chance to discuss the noise, but basically that is sometimes for reasons either we do not want to model or we are not able to take into account in the model. There are variations between the in the target in the data, so we cannot reduce the noise. We cannot just throw away noise. There is some factor outside our control. Basically, that is the understanding. So the correct answer is that when there is noise, simpler models are more welcomed, because in the presence of noise, more complex model family, which means if you have a larger family here, it is more likely the learning will arrive in a situation that it select one candidate that is very superly better at modeling, at describing the coincidence relationship in the coincident relationship in the data sample that caused by the noises rather than the trend. Okay. And the other statements are wrong if the data model can achieve 0 errors on the training data, doesn't mean anything too much. And if we collect more data samples, we can get rid of the noise. No, noise is intrinsic. We cannot have control on that. And when the target values are raw numbers, the noises must follow a Gaussian distribution. No, not necessarily. Noises can be different distributions. So summarize, E out unknown cannot be computed. E in random can be computed. Question 2. For the first way of measuring the cost, we have 1 and 0. For the second way of measuring the cost, we have a negative log 0.3, which is positive 1.11. And for the second part, we have a negative log 0.34, which is 1.08, this one. And for the question 3, when there is noise, simpler models are better. Okay. So yeah, so much for today's discussion. I appreciate your effort. I know this discussion is highly abstract. So if you still have questions, you are welcome to stay for a little bit longer. I hope we can demonstrate you a little bit more intuitive examples. And in any event, so our main point today is learning is a stochastic, it's a random business, okay? And the randomness or the stochasticity is mainly from the fact that we have no control of what bag of training samples we are given. That is given to us. And after being this is given to us, even everything else is fixed. The result of the learning and the application of the result of learning on any test point, test sample are stochastic. So we have some kind of guarantee of if we have collected a large number of samples, the evaluation of the learned hypothesis will not give us a big surprise when it's applied to the test environment. So yeah, that's it. Any questions? So you are free to leave now. I'm sorry we have been maybe 4 minutes over time, but if you have questions, you can stay. And even if you do not have questions, you can stay as well, because I'm going to show some very interesting behavior of simpler and more complex models. Okay, well, as I said, there is the argument goes to the argument to limit the probability that we end up with a huge surprise in test environment depends on we have a clever way of counting the number of hypotheses. Why is this? Think about this way. Given the Hostings inequalities guarantee, which is this one. I'm just writing down here. So I just write P. Bed H, that is less or equal than 2 to e to the power 2, which is super nice. Well, if I have two H1 and H2, and I don't know what I'm evaluating, I maybe end up with H1 here, or maybe H2 here. So a simple way to do that, okay, I have P bed H1. I just write a small value here, okay, and I have P bed H2, okay. Well, then I have an argument like that. Okay. Okay. That must be smaller or equal than 2 delta, right? Consider that. What is delta? Delta is the portion of the red bags in my magic realm. Okay, so this is a delta. This is another delta. To let the bad thing happens, either one of the bad thing happens, to let the equal sign hold, then we must have the thing is the one thing we must have is any bag that is bad for H1 is good for H2, right? They don't overlap with each other. So when I count the joint area, we just add up them respectively. If there happens to be some bag, like bad for both, then I will have the less than sign here. Okay. So I can limit the chance of bad thing happens using this argument. However, the unfortunate fact is even for the simplest model family, for example, our perception family, okay, sorry. This question, how many guys in the perception family? Well, consider that each of the flat card is 1. So maybe that is minus 1.5, 1, Okay, this is 1.2. This is maybe 0.1, 1.5. So basically, if I change a little bit of these parameters, I have a new hypothesis. So the answer is infinity. Well, that is very unfortunate, right? At the end of the day, if I want to multiply a factor to, well, limit the chance of bad thing happens, and the factor to the bad guys is infinity. I don't like that. So some very smart people proposed solutions that maybe we do not need to individually consider each hypothesis, because in a family, when the family is regularly constructed, the behavior of the hypotheses are so closely linked, which means if a bag is bad for one hypothesis, it is bad for a huge subfamily of the hypotheses. So basically, you get this situation. Here, a lot of overlaps. And following this line of argument, people find that it is how many diversity of the family on limited number of samples, which you can call dichotomies. Oh, no. Realized dichotomies is really important. What is dichotomies? Okay. If I give you 3 slots, you have 8 maximum dichotomies, which means you can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 8, maximally 8. If you have 4 decisions to make, maximally you have 16 dichotomies. So easy. Basically, n samples can accommodate, can maximally have 2 to the power of n dichotomies. Okay, that is a result of doing classification on the n samples. Maximally, you have 2 to the power of n possibilities. And why this is important? Because some families that is simple enough cannot realize that maximum number. I'll give you an example. If the size are here, okay, and we consider the perception. Dichotomy 0, 0, 0, 0. Okay, realizable. Okay, dichotomy 0, 0, 1, 1, realizable. Dichotomy 0, 0, 0, 1, realizable. However, dichotomy 0, 1, 1, 0, which means 0, 1, 1, 0. This is non-realizable, as we have discussed. So the maximum number of dichotomies realized by perceptions on 4 samples, that is less than 2 to the power of 4. It's less than this. And there is a very nice theoretical argument that if you can find any number of samples, for example, in this case 4, at this number, this happened, we can see, okay, you give that hypothesis family really a big challenge. So much so that it breaks the hypothesis family. And there is a conclusion, once break, always broken. So for whatever n greater than 4, the maximum number of dichotomies that could be realized by perception can never catch up. And the conclusion is it does not only cannot catch up, it must fall behind so much. It falls behind very much in polynomial terms. Okay. Then that comes the beautiful part. When the factor here becomes polynomial, and when the n grows to the infinity, okay, you can see, because the decrease is proportional to exponential to n, and the increase is proportional to a polynomial with respect to n. So when you combine them together, we will have this drops to 0 when n grows to infinity. That means, okay, when you have infinite, you have large enough training sample, you will have the guarantee of learning. And that is one of the most beautiful theoretical achievement in machine learning. Okay. Well, to investigate the different numbers of behavior a model family can adopt. Let's see an example. I should have, if I have time, I should demonstrate the example on class. But unfortunately, the discussion is very lengthy. So, yeah. I'm using a logistic regression model. I think I just copy because I have missed the setting up here. I copy it here. Okay. The connection was interrupted. A bit slow. Okay, that's not matter. I think I have already saved the result for you to view. You can experiment with these cells back home. I have implemented linear regression, neural network for comparison. When I apply the model, you cannot see too much difference. However, what I'm doing is I have flipped a subset of the labels, which means I introduce some noises. In this case, you can see for the linear model, the behavior does not change too much. For a simpler neural network, it starts trying to catch the flipped symbols. And for a more complex neural network, well, you can see the capability of adaptation of the model family is so huge that it adapts to these, broken regions. This will achieve very high training errors, training accuracy. However, you can imagine the generalization won't be very good. Okay, so that is what I'm going to see today. Okay, I have a quest. Yeah, if you are still here, I said I will take a consultation hour next Wednesday, from 5 to 6 p.m. as usual, and I have marked that in the announcement for this week. Okay. Sure. Okay, if you do not have more questions, let's wrap up here. Thank you very much for coming. And I know today's topic is a bit theoretical, but I hope you enjoy the intellectual journey. Okay, welcome to the world of real machine learning.
Professor?
Yeah, have a nice still that week. Bye-bye.
Hey, hi. Hello?
Questions?
Yeah, I have a lot of questions about the week 5. Can you share the screen?
Give me a sec.
Okay.
I think I need to stop sharing my screen first. But where is my screen sharing? Okay.
Oh, I still cannot share the screen. The host disabled to.
Okay, now you can.
Okay, thank you. Where's? Oh yeah, I need. Is this one? Wait a minute. Oh yeah, can you see my screen?
Yeah.
Yes, I have a question about Wi-Fi oh yeah, this one.
Yeah.
What's the meaning of the learn if the y is less than 2?
It's just a safeguard. let's think about that. If
Yep.
you are talking about, let me do things like that. Okay.
Yeah, it's a
We're trying
it's
to look. It is something like if you given negative, negative, positive, positive, negative,
yeah.
things like that. You want to calculate the entropy, right?
Oh yes.
And here just means if you happen to have a thing like that, which means nothing, or you have a thing like that, positive, or you have a thing like that, negative. That includes these three situations: nothing, one sample, positive, one sample, negative. In all three cases, the entropy is just 0 because there is no uncertainty here.
And one question is about this one is general reliability is 1000 to 0.5 and 1000 to 0.01. What's the meaning?
Can you let me ask you? Can you copy this?
And this.
Yes, copy that.
Oh. Yeah.
And can you add a new cell here? Yeah, paste it here. And yeah, of course, make it, change this, no, change this. This is too large. Change it to some manageable thing, like a 50 or something, that anything that you can comfortably examine, yeah? Just go.
Oh.
You need to define that, maybe?
Yeah, to run. Oh. And why?
No. It complains the function hasn't defined. Can you refer to our class?
So I need to run all the code.
This one. Just always this one. Yeah, now you're done. Okay.
What is?
Yeah. No, not this one. Just around this.
Oh.
Yeah, you can see.
Oh yeah.
Okay, and well, you can then put this list here, which means, yeah, if you do not understand one thing, you construct it bit by bit by yourself, then you will understand. Do this. You just type list, yeah, and parentheses, yes. So you see, what you have done is just to take apart each of the bit into independent zeros and ones, and you can then put this here. Yeah. Okay, so it's not very surprising. It's just to wrap it into a table that is easy to
read.
To manage, right? Yeah. Okay, now you have put everything here into the y here, right? So can you just write y equals this, let it to be y. Okay, now you have y, right? Okay, and then you do this, right? Okay, Can you copy this? Copy this.
This one.
Yeah. Yeah, down the Y. Yeah.
I
Yes, a
mean,
new line. Yeah, new line here. Yes. No, 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 no.
oh,
It's wrong. Yeah, now it's right. So
oh,
you get it? And well, then you see, now you have a wrapper of NumPy array here, right?
yes.
Then just copy the frequency equals NumPy array here. Copy that part here, which actually, to be honest to you, if you really want to learn things more efficiently, you do not copy. You type it by yourself. It helps you very much.
Okay. Oh, I should copy number the area.
Yeah. Okay, then you can print the frequency. Yeah. Right. And now you can consider how this, because this is the easy part, but this part,
Yeah, I know what this means.
okay, then you got it. And well, if this part, sorry, this is okay. Then try to change the parameter here. Okay, you do not need to be exact to be, yeah, anything you want to try, yeah.
Oh,
But maybe you are too fortunate. Change it to, yes, run it again, maybe.
mm,
See, now the estimation is not the accurate one, but that is really, really normal. Just run it again, things will change.
Mm.
No, just run it using the same parameter, just run multiple times.
okay.
Yeah, run the same thing. Click here.
Always send.
The same. Maybe I have set the random generator to get a predictable result. You can change the random generator. Anyway, you now get the point. Okay.
Yeah, I get.
When you get something that is not understandable, try to try to investigate, examine the program from outside, inside. Yes, this is where you get the understanding very, very comprehensively.
Because I know what's the meaning of the decision tree series, but I'm not very good at Python, and I don't know how to use Python to make it. It's a little bit hard and for me.
Okay.
Then I think this is what's that? Oh yes, I still the last one question is about what's the FR meanings.
I think similarly. Can you? So, okay. Okay, can you stop scrolling so I can show you?
Okay.
Yeah.
So
Can
stop
you,
sharing.
yeah. Can you take some sample to execute sample and one feature and value counts, and then you will know what does this mean. This means to okay, please just for example, is this your sample, right? DF, okay. You use DF temperature value counts normalize equals true. Yeah, you can just copy this.
This one.
Yeah.
And equal to DF.
Yeah, change that to DF. No. You already have DF. Change the samples to DF.
Okay. um,
You do not have this one. Yeah. Yeah, try.
oh, no.
Do you have the
Fine.
DF defined?
We do run it core. On the core.
Okay. Just run this, and then you are good to go.
Oh,
Not okay. Don't run away. Not feature. Use any one of these, like temperature, look, something. Replace this with outlook or temperature or anything.
oh.
You need to code it.
You mean I code it?
No. You need quotation.
Oh,
You
yeah.
need quotation marks. Yeah.
And run it.
Yeah.
Oh.
See?
Yes,
Okay. Well, we'll go a little bit up. See, put this into a variable. Maybe you can just let it to be values or something, anything.
copy this one.
Yeah.
And to here.
Yeah, just give it a name.
And we can change value 1.
Doesn't matter because this is inside
Yeah.
a function, so this is
Mhm.
okay. So yeah, then just write a for loop of this. Copy this. Yeah, here. In value 1. And don't copy other things. You just need to print V and FR. Then you will get it.
So I need to print. Like, is it like this?
Yeah, just run and see what happened.
We copy.
No, not the same thing. No. It's different.
Or maybe I.
Wait. No. Wait. What is this comma? Is this a Chinese comma or a English comma?
Yeah, base English comma.
No, I don't think so. Change the comma.
But this comma is things like this.
No, you just type a comma here, please.
Okay. Like this. And I change, but
Yeah.
and then run it.
Yeah.
Oh, yeah. Oh, yes.
So now you can see that then you need to compute the entropy of the subpopulation. So next difficult part to understand is this one, right? Okay, so maybe you copy this part here. You do not need to compute the entropy. You just need to understand on which samples you compute the entropy. So you just need to copy this.
This one.
Yeah. No. The indentation is wrong. It's wrong. The indentation is wrong. You need to put some. Don't scroll. You need to put. You need to put them together.
All together. Oh.
No. What I mean is, you need to remove the spaces here, and yeah, remove all the spaces.
Really?
Yeah,
This one?
remove and use the tab to align that. Use the tab. You have a tab. You just click tab.
Tab. Okay, tab.
Yeah,
Yes.
and do the same for this one. Yeah, and well, this will not give you anything because you haven't printed. You can print the samples here. No, you print. You add a print here.
Oh, okay.
Yeah. Yeah. Sorry, not samples. You now have the name. Don't scroll everywhere. Okay. You have the df. Use df to replace the samples. Here. No. Here.
Oh, yes.
Okay. This ATTRs don't scroll everywhere.
Okay.
This attribute is actually this one. Because in the program, you have looped over every attribute, but here you have specified that to be auto-loop. Okay, use auto-loop to replace this attribute. Then you get the point. Quotation. The quotation, yeah. Okay.
Run it.
Yeah, now you can run that. You will understand what target. And the target is another one. This is a play. Play is a target. Yeah. You also need to code. You need to code.
What's code?
Code the play.
Oh.
This is a string. Yeah. So you see, in the first loop, you consider when Sunny when Outlook is sunny,
Yes.
and you select a subpopulation for the Outlook is sunny, which is 0, 1, 6, 7, and 9, 0, 1, and if you look at something here, you will find this is the subpopulation here. Okay, and in the second step, you will find if the outlook happens to be overcast. And in this one, if the outlook is rain, that means you have split the data according to the outlook into 3 subgroups. Okay.
Yeah, I get it.
So
yeah, maybe I will try to code it after class.
Yeah. And maybe you can after the class, when I have upload the recording, you can play back, and we'll try to understand what's going on here.
Yeah, I always review your recording.
Okay, thank you. And what I mean is to review the conversation we are having now.
Oh yeah, sure.
The specific one, I'm helping you doing this this part.
Okay, thank you.
Okay. So have a great week. Okay.
Okay, bye.
Bye-bye.
Bye.